Welcome back to the Intel Booth Theater here at Supercomputing 2024 here in Atlanta, Georgia. We're so glad to have you here. As we've been saying throughout the show, we are going to have great presentations happening with our partners to tell you about what Intel is doing in the ecosystem. We're so excited to have here today another presentation starting right here, right now. It is entitled The Role of SYCL in the Machine Learning Assisted Gigantic Image Cancer Margin Scanner Project. Here to give that presentation is Alper Sahistan and Dr. Valerio Pascucci. Let's give them a round of applause.
Okay, thank you very much for the introduction. So we're going to talk about this project recently awarded by the ARPA-H agency, and is a project focused on analysis of data from colon and colon cancer data. And this is a multi-institutional team and different organization. And the University of Utah, in collaboration with Intel, is focused on the development of the cyber infrastructure for the machine learning analysis of data from surgeries. The goal of the project, this is kind of the team across the different institutions, is to take prostate colon cancer data, this is data from surgery, and imaging so that the surgeon can detect potentially remaining cancer cells during the surgery so that they can actually finish removing the data, the cancer at the margin, and complete the surgery without anything left behind. Avoid the risk of doing follow-up surgery or recurring cancer. There are different ways of slicing through the images, and this is part of the project. This is the type of data we were dealing with. The data is very hard to analyze. You need a histopathologist looking at the information, and typically this would take 1 or 2 weeks to come back. The challenge here is to analyze kind of billions of pixels in real time, and within 10 minutes, so giving time to the surgeon to intervene, being able to provide the answer needed. And so the solution is that then to use new technology in terms of both the data acquisition, getting the information, imaging directly. We have to introduce a new scanning device that physically is going to have like 20 times better resolution than the current best state of the art. And within the operating room, immediately get the information. We have a new instrument that allows to rotate, this is the case of the prostate cancer, and get sequences of images that allow to find everything at the margin of the surgery. So the data is going to be very high resolution. This is the type of images that we're dealing with. As you can see, the level of resolution and panning that one would need to go through is kind of very high and impressive. And if you had to deal with a human dealing with this data this quickly, it would be impossible to get the results that we're looking for. So we're building the cyber infrastructure to collect the data, imaging, and get the information extracted automatically. This is the details of the size of the cancer region that's typically being extracted. And that's how it's been turned into images, looking at from the different perspective and looking at the quality of the information that needs to be extracted from the different point of view. And so this is kind of all the images that we'll have to deal with automatically. And practically, you will have large sequences of images with this type of coloring, where the AI will have to replace the humans in detecting the information in the different location. Here you see the level of zoom and the details that need to be extracted at different stages of the analysis. So this kind of give you the story of how the image has to be analyzed. You see the different regions, how the needs to be detected. It's very hard to tell the difference, so we're going to collect over a petabyte of data, and that will be trained through GPUs and CPUs concurrently at the same time. This is the device that will be deployed at the end with a new images infrastructure in collaboration with Instapath, is a company, and we'll have a new system where through a set of patterns allowed to actually get images of high resolution that was physically possible before. And so this is kind of the coloring that we get out of the results. Overall, this is the cyber infrastructure where we'll see the high-performance computing platforms, imaging data that has to be collected. It goes into a large-scale training environment, and then at the end has to be deployed into the operating room with that for the use directly from the surgeon. And now Alper is going to talk about the use of the SYCL infrastructure to get the data through the infrastructure with compression and fast delivery.
Hi. So first of all, we need to motivate why we need compression. So as Valerio put in, the data is huge, so we have to somehow get the data in the processable amounts. And like most applications these days, you care about your device memory and your transfer times as opposed to you care about your compute time. So this is especially true for your GPU kind of processing as well. And compression is a way to combat these memory constraints. And we work on we worked on converting the ZFP into SYCL. ZFP is a lossy compression algorithm for floating point and integers that is in the multidimensional arrays, and it's particularly tuned for scientific data sets. It is very similar to JPEG compression for images, but as I said, it's tuned for scientific data sets, and it was developed in Lawrence Livermore National Laboratories. The ZFP has three main compression strategies, two of which being under variable rate mode, and today we're going to focus on the fixed rate mode, which is storing fixed number of bits per a floating point number. So if you're compressing with bit rate of 4, then your 32-bit single precision floating point numbers will each get stored as 4 bits. Of course, the algorithm is elaborate and tries to preserve the information as much as it can, but it's a lossy compression algorithm. So let's give a broad overview of ZFP and how it works. This is by no means an extensive explanation, but this is to make sense of what we did and what our efforts were and how we what we needed to do. Let's begin. The algorithm starts by block partitioning the data set into 4 over D blocks, 4 over D meaning the dimensionality. So if it's a 2-dimensional data set you're compressing, then it's going to be 4 by 4, i.e. 16. If it's 3-dimensional, it's going to be 4 by 4 by 4. And then each block is assigned to a work item, ideally a thread, and those threads start processing and compressing the data. So after that, we convert the floating point numbers into a fixed precision, fixed point format, which is block floating point representation, where each number is represented with respect to the largest mantissa within that block. And then those numbers are then go through a decorrelating transform. This is a form of discrete cosine transform. This allows us to compress the numbers better. And then we go to a very simple step called reordering by sequency. This is a very simple step, but I would like you to keep this image in mind because this gave us some challenges when we were porting the algorithm to SYCL. And then there is a conversion from signed integers to negabinary representation. This representation, instead of using a base 2, we use -2 as a base. After that, we go to we transpose the numbers, a list of numbers to have a list to most significant ordering. And then each bit plane is, until now, compressed losslessly using embedded coding. I know this might be overwhelming, but you don't have to comprehend the algorithm fully to understand what I'm going to say next. And then after this, embedded coder emits one bit at a time until a criteria is satisfied. This criteria, if you're working with fixed rate, is going to be emitting that amount of bits, then it stops. So if it's a 4-bit rate, then you're going to emit 4 bits for each floating point number, and you're going to stop. So we started the project by translating the already existing CUDA implementation to SYCL using Intel's data parallel C++ compatibility tool, DPCT in short. And this is the command we executed. It's as simple as that. If you have an already existing CUDA project, you can run a similar command like this, and all of your CUDA files will be translated to SYCL, and then you can start working on them. Of course, there were some small problems. I'm pretty sure they resolved this issue already. We worked closely with the support team and the Intel engineers. But, well, if you encounter this kind of problem where your CUDA header files are not getting picked up, you just can rename them to CUDA files, and the tool should pick up. Well, the DPCT tool is a rule-based converter or translator, so it's gonna ask you to sometimes convert some of the lines or fix some of the translations manually. Like as present here, it's gonna warn you with a comment within the translated code. And in this case, there is a mismatch between the concepts of error handling between CUDA and SYCL, and it like has a no operation kind of error handling statement that is inserted here as a dummy, and it's telling you to fix this with some manual effort. Well, SYCL uses try-catch statements to handle these kinds of exceptions, so you can just rewrite this as a try-catch block. There will be like numerous, we encountered at least numerous like these kinds of like minor adjustments that we had to make, but most of them were easily resolved within a couple of minutes. Then there are also like more significant conceptual differences like memory model. First of all, SYCL offers 2 different memory models, one of them being the buffer memory model, which gives you more error handling but has more overhead and slower. And the other one being unified shared memory model, which is in short USM. USM has less overhead and it shares more similarities with CUDA memory model. And that being said, there are still, I think, mismatches in some unmapped features between CUDA and SYCL, and one of them being device static const arrays. These are arrays that you can make use of as lookup tables and like do some transformations. Do you remember this image that I told you to remember? Well, so this is implemented as a device static const array in the CUDA implementation. Since SYCL doesn't have that, we had to find solutions to that. We attempted the most wasteful solution maybe, which is allocating this static table every time, do the transformation, and deallocate it after the kernel execution was done. Of course, this is wasteful and slow, so we got in touch with the Intel engineers and the support team, and they suggest that we use their experimental device global allocation method. This, although worked on certain GPUs, we opted out for a third solution. I will come into the next slides when I'm talking about the optimizations, at least one of the optimization steps we took to improve the throughput of ZFP. So the problem we encountered after we got the code running was register spilling. So let me recap on what register spilling is. Let's imagine you have cups like these suspended in the air, one layer on top of another. And if you start filling the topmost cups with water, it's going to overflow at one point, and it's going to go down to the green and the lime cups, and it's going to overflow them, and eventually it's going to reach the orange cup. Let's imagine these are not cups, but your memory units, your registers, your L1, L2, L3, and L3 caches, and your RAMs. And let's imagine now you're not overflowing water, but your data is kind of spilling down. This is register spilling. The reason this is bad is now your application has to wait from your slower memory units to fetch the data to your faster memory units where you actually process things like your registers. And that's bad because your application tends to be more memory bound as opposed to compute bound. And that limits what you can achieve in a limited time. So we had to solve this. And this is especially prominent. This was especially prominent when we were compressing 3-dimensional data sets because it's using a larger block size, as you remember, 4 by 4 by 4, so 64. And imagine you're compressing double precision, so double the size as opposed to single precision. So what happened as we realized this was like we attempted several solutions. First one being using the large register file mode, which is a compile time option. You can tell it to the Intel compiler to use that. What it does is it disables half of your execution units, halves your processing power, but gives you the unused register file from the disabled unit, and then you double your register file space essentially per execution unit. Not ideal, but it works if you're like fiddling with, if you're dealing with some sort of register spillage issue. Well, this gave us some speed up on especially three-dimensional kernels. But that being said, it wasn't up there for us yet. So we attempted a second solution, which was, do you remember this table? Again, it came up again. So this is the third solution that I was going to mention. So here, instead of like having a for loop over an array and like doing that transformation that is presented in the arrows, because those arrows are a lookup table of size 64 if you're dealing with three-dimensional arrays, which contributes to the register pressure. We did some people might consider something ugly, which is we wrote a function that is 64 lines long, and we are doing those swaps without a for loop or an array. We're just doing that, and this gave us some speed up. Especially on two-dimensional kernels, which we weren't expecting. So since we were targeting three-dimensional kernel speedups, like if you can see the yellow like bars, we were trying to get them up. So what we ended up doing was going for a third solution attempt, which is, do you remember these type conversions? We start with like a float or a double value, and then we turn them into a fixed block floating point representation. That's an integer floating point to integer conversion. And then there is a signed integer to negabinary conversion in the step 5, if you remember from the earlier slides. This is another conversion. So this happens per block basis. So each of these data type, each of these conversions are stored in separate arrays of size 64. This also contributes to the register pressure problem. So the solution we crafted was using a simple C++ union and combine all of the types. Since these types don't depend on each other, they were just being written from one array to another. This is a viable solution. And essentially now, instead of doing this and allocating this much memory, we allocate a single array that writes in on itself, and this kind of mitigated a lot of register pressure, and we increased our throughput by over 2x. By the way, yeah, we are measuring the performance of the application by gigabytes per second processed per each kernel with bit rates. Bit rate meaning the compression rate of the kernel. And let's finally look at the final table. We started with the leftmost one tables with two different data sets, one of them being Miranda and the other one being Next. And as you can see, especially the higher dimensional encode and decode kernels are kind of low. This is the Bayer translation, and then we worked optimizing the code and improving the performance. We got in touch with Intel people and got support, used their toolkit to improve our performance drastically. We're still working on this to get it even more competitive with the hardware-specific implementations. But let me remind you, SYCL is cross-platform, so there is some benefits, although maybe performance might be slightly lower than the hardware-specific implementations of ZFP right now. Yeah, I will give it back to Valerio now, and he can wrap up.
Okay, thank you, Alper. So, but generally speaking, as you can imagine, as part of this large cyber infrastructure where you have to run through images in various convolution filters and classify different type of cancer cells and so on, the performance of the entire pipeline depends heavily on the level of compression, and especially part of it is related to the I/O as part of actually the movement in memory. And so, generally speaking, we are now having our first pipelines with the images. Now the advantage is primarily in getting the data loaded and compressed, and then we're pushing more and more, going through the entire layers of inference to get even further performance advantages. On top of this, we're looking at segmenting the data and finding region of cancer through topological priors in the machine learning process. And so the images get segmented like this. This is what they call the Morse-Mail complex. And then through this, we can actually segment the space at different scales and then quickly identify and allow the machine learning process to not work at the level of single pixels, but region like this, which also speed up the process in a significant way. And so at the end, this work will require a collaboration between people in the computer science space, machine learning experts, but also clinical teams. And then we're going to use a set of interpretability and explainability dashboards where we allow, through visualization techniques, to help both improve the internals of the machine learning algorithm, but also help the clinical teams, doctors, pathologists, and surgeons to actually use the tool effectively without necessarily becoming an expert in the AI field, which is typically kind of a major process. And this concludes our presentations. Again, this is a large collaboration between different institutions and range from collecting the data, going to surgery rooms, developing entire assembly infrastructure, and central this has been speeding up through use compression techniques and the Intel technology. And thank you very much.